Hello everyone, my name is Wenjun Xu. I'm a fourth-year PhD student from National University of Singapore. My research centers on surgical robotics and in particular using data-driven approaches to automate and control a class of flexible surgical manipulators. And here are some examples of flexible surgical manipulators. The advancement of such technology has enabled a lot of new surgical paradigms, such as single-port surgery and natural orifice transluminal surgeries, because they are mechanically flexible and they usually adopted elastic elements to enable continuum bending, and they're curved linear, so they can be easily navigated through tortuous and confined human lumens, and they're extremely downscaled so that they can be inserted into human cavities such as oral or nasal cavities. And they usually adopt non-conventional actuation mechanisms such as cable-driven or pneumatic hydraulic-driven. And though most of them are in research stage, some of them have actually been commercialized. Here is 3 examples of the commercialized platform. The first one, the Flex robotic system from MedRobotic. It is used as a flexible trans-abdominal and trans-thoracic robotic scope. And the Monarch platform from Auris Health, working as a flexible bronchoscope. And probably the most famous one, the DaVinci single-port system, which is the latest generation of the DaVinci family. It features fully wristed elbowed instruments and fully wristed endoscope. It has been cleared by FDA for urological procedures. Despite the various advantages over the rigid manipulators, they suffer sufficient nonlinearities and hysteresis, mainly because of the adopted elastic materials and the actuation mechanisms. And so modeling and controlling such systems is extremely challenging. And also their working environment is usually confined and tortuous. And the system itself usually consists of multi-degree freedom, and it is redundantly actuated. So with these challenges, it's extremely difficult. Analytical models are extremely difficult to obtain, and they are usually insufficient. So here comes a learning-based or data-based, data-driven method. So I'll introduce 2 learning frameworks. So we aim to automate certain routine surgical tasks. This figure shows the level of autonomy in surgical procedures. The most mature surgical systems nowadays are controlled directly by surgeons. And we call this mechanism teleoperation, where the surgeon operates a master console and their commands can be translated into the manipulators. However, such mechanism is prone to human errors, such as hand tremor and human fatigue, and which affect the accuracy and efficiency of the procedure. And so it evolved to a shared control mechanism in which the human is still in the loop, still operating the master console, but the robot can react automatically in certain conditions, such as in an unsafe area, by using methods such as virtual fixtures. However, we agree that since in this mechanism, human is still in the loop, it is still prone to human errors. So we agree that supervised autonomy would be the most promising solution, where the surgeon executes the higher level surgical plannings and the robot can execute the planned strategies faithfully, and while human surgeons only takes over the control in critical moments. So I'll introduce the first framework that can achieve such a level of autonomy, which is enabled by learning from human demonstrations. The tasks we aim to automate are inspired from these 2 clinical related tasks. The first one is a tube insertion task, where the robot, the flexible manipulator, has to insert into this curved tubular environment it is a common procedure in transoral or transnasal procedures, as well as natural orifice transluminal surgeries. And the second one is just to follow a marked pattern and to cut the tissue en bloc. And this is a general framework of learning from demonstration. Firstly, the human expert performed the task several times, and critical trajectories will be recorded. In particular, we learned the trajectory in actuation space. So actuation space trajectory will be recorded, and then the trajectory will go through necessary data processing procedures like smoothing, filtering, time alignment, or for tasks that involves multiple segments, segmentation will be conducted. And then the prepared trajectory will be modeled by machine learning methods, in particular with Gaussian mixture models, which is commonly used to model human behaviors. And then we can review the underlying trajectory properties by GMM. And afterwards, with the model, we can generalize a smoothed path with Gaussian mixture regression. Then the generalized path will be input to the surgical robotic system, and the robot can execute the task automatically. So here is the learning process for the first task, the tube insertion. So we actually built a tubular environment with plastic tubes with different curvatures, 60-degree bending angle and 90-degree bending angle. And here I plotted the Gaussian components. The green ones are the Gaussian components in the modeling process, the GMM, and these blue ones are for the Gaussian mixed regression, and they are plotted in 2D just for visualization. And these zigzag trajectories are from human demonstrations. Well, with GMR, we can generalize a very smoothed curve, so it is potentially superior to human demonstrated examples, and they are smoother and they are more efficient for the robot to execute. Okay, the learning process for a circular cutting task. Since this task involves multiple subtasks, or we call motion primitives, we first use supervised learning method to segment the subtasks. And for each subtask, we again employ GMM and GMR for modeling and generation. So here are the three motion primitives that's evolved in this task. Okay, this video shows how the robot is able to automatically execute a desired task with the LFD framework. So the robot inserted into this tubular environment automatically. And the second tubular environment. This is a multi-motion primitive task. Okay. First step, the robot has to advance toward and to reach the target. Then it bends. And then it followed the marked pattern. Okay. So for the previous study only considered trajectory properties, but for surgical manipulators, interaction or manipulating soft tissue objects is almost inevitable. So a framework that also considers force requirements is proposed here, enabled by reinforcement learning. Okay, the expiring task is a palpation, where we aim to automate a crucial step in the palpation task. The robot tap the tissue and establish contact with the tissue and in a confined region, and to deliver or apply a gentle force to the tissue. So the palpation is practiced by experienced physicians to examine the mechanical property of a tissue element so that to locate diseased region, since the stiffness of diseased region is usually higher than those normal tissues. So this task may seem intuitive, but it is actually challenging to perform, particularly for those flexible and continuum robot, because it involves multiple requirements and multiple constraints, and it is the non-linearities I mentioned before, as well as high dimensions and degree freedoms. Actually, so this is the robot we built, a hybrid robotic system that contains a soft finger element and a 6-degree freedom manipulator for positioning, and it was sensorized by physician and a force sensor, and it's cable driven, and it is redundantly actuated. So we came up with a learning framework based on reinforcement learning. So in reinforcement learning, we have to model the problem as a markup decision process, which is represented by state, action, reward, and state-to-state transition probability. And the goal here is to optimize, to maximize the expected return represented by Q here, and by finding a optimized policy pi. So we use a particular method called policy gradient to learn and optimize the policy. This is how the gradient can be computed. So this framework is particularly suited for our problem because it is model-free, and there no prior knowledge of the system as well as the environment is included. And it learns to acquire the skills by trial and error, and it can train a feedback control policy. It can also coordinate multiple objectives and constraints by carefully shaping the reward structures. And it's suitable for high-dimensional continuous state tasks by introducing the neural network representations. However, such framework is it's very difficult to train a real-world robot because you have to consider the safety issues by avoiding collisions. And also another issue is data efficiency. Usually reinforced learning requires a lot of training time to finally obtain an optimized policy. So in order to facilitate training the real-world robot, we introduce a safety check routine by using a pre-trained finger curvature model for predicting whether the collision is likely to happen or not, so that we make sure that only safe commands are sent to the robot. And to accommodate different tissue surface conditions, we introduce a random initialization process so that the robot can learn adequately different surface normal conditions. Okay, we first implement the framework in simulation to test its feasibilities. And we carefully shape the reward structures by accommodating different requirements like the distance, force, orientation requirements, as well as different constraints. And these figures show the training performance. We plotted the average return. It increased steadily and finally can converge to an adequate value. This implies that a optimized policy can be learned. And by the collision check routine, we can sufficiently reduce the collisions.
5 minutes.
Okay. To evaluate its generalization capability, or in other words, to test whether the training policy can be applied to different environments. We applied the policy training in the previous slides to an unseen environment. We changed the environmental conditions by varying the initial orientation, the tissue stiffness, and targeting force, and the initial distance between the tissue and the finger. So these figures actually suggest that the training policy can succeed the task in unseen conditions. So this implies that it has good generalization capability. This is particularly favored in clinical or surgical conditions where changes of environments are likely, such as the movement and deformation of tissue, and also an unknown tissue stiffness. Okay, this video shows how we implement the framework to this hybrid robotic system and how they can learn and optimize the policy. And finally, it can learn to tap the tissue automatically. Oh. We applied the training policy to 2 different environments several times to evaluate the policy, and for most of the time, the policy can succeed the task. Okay, here comes the conclusion. So I presented 2 learning frameworks, the learning from demonstration and reinforced learning to achieve a supervised autonomy, and particularly for flexible and continuum surgical manipulators. And the frameworks has been tested and implemented on the real-world flexible robotic system in our laboratory settings, and they suggest promising results. However, in order to evaluate further the efficiency of such framework, we have to build more realistic surgical environments, and also in vivo tests are demanded. Also for future adoption, safety issue should always be the highest priority when executing surgical autonomy, and this should be a very important and promising direction to investigate. And also integration of advanced sensing and imaging modality would be beneficial for tasks in complex conditions. Finally, I would like to acknowledge the sponsor for these projects and my affiliations and labs. In particular, I'd like to thank my supervisor, Dr. Hong Liaoren, and all my collaborators who have contributed to these works. And thank you.
Thank you, Wenjun. Who starts? Okay.
Thank you for the nice talk, and this is a very complex problem you're tackling, so I think you have a very nice approach. I guess my question is about shear stress. I think in interaction with the environment, the normal force is important, but also the shear stress. You might damage tissue by having lateral movements. Do you try to find policies that maybe minimize also shear stress, or that's not?
We set the constraints to the shear forces. It cannot exceed certain limit.
So you have a threshold. Okay. And that might depend. Sometimes shear stress can be good. Sometimes you even want to manipulate a bit and move things around. So I guess you will attune it a bit depending on what type of surgery and what type of tissues you manipulate.
Actually, we just applied it to artificial tissue made by silicone.
Mm-hmm.
But we manipulate the stiffness. Some is hard, some is soft. So it's a very artificial environment. You haven't applied to a real tissue yet.
Okay, yeah. That was then maybe my next question is indeed, I guess the next step will be to try on animals or porks or something.
Probably.
Is that coming soon or not yet?
Not yet, but we are planning. Yeah. Thank you for your question.
Okay, thanks. Yeah.
I mean, considering the navigation capability, did you do any comparisons with the state of art based on imaging like fluoroscopes or sensors placed on the robotic manipulator?
Yeah, we sense, the robotics is integrated with sensors, position and force sensors. And we haven't compared to the imaging sensors. Because the sensors here are the information from the sensors we integrate is already adequate for our planning. So
if you didn't have any learning at all,
learning,
then
it learns.
The performance. Do you have any
Comparisons? Not yet with the ones that integrate with imagings.
One more question? No? Good, then Wenjun, thank you once more.